Welcome in our today's mathematics class, where we are still going on with the algebraic expressions. And today I want us to look at equivalent algebraic expressions. We have seen about the algebra, and we actually looked at expressions where we were able to look at the pronumerals. Now today I want us to look at how can we tell that algebraic expressions are equivalent. Now just to look at a few, as you can see, like if you are told the sum of x and 4, the word is the sum of x and 4. If you are to write this as an algebraic expression, then it will mean you write x plus 4. Someone else will choose to write 4 plus x. Now, but at the same time, we can also have it written maybe as x plus 1 plus 1 plus 1 plus 1 4 times. Now, you realize that the value of each in every case is the same. So we are trying to just say that all these expressions that we have are equivalent. They are equivalent simply because they give us the same values. For example, if x in every case, if we said that x is equal to 0, so if you take x is equal to 0 and you replace here, you'll find the value here is 4, the value here is 4, and also here is 4. If we change again, the same will apply. Now, to illustrate this issue of equivalent algebraic expressions, we are going to use a table and substitute the values of the pronumerals at every given interval, and then we see which expressions are going to be giving us the same answer. If the answer is the same, then we shall say that this expression that gives us the same answer when substituted with certain values, they are equivalent. So let us look at the table that follows. On this table that we have on top here 4 expressions. The expressions are 3a plus 5, 2a plus 6, 7a plus 5 minus 4a, and finally a plus a minus 6. These are expressions. From these algebraic expressions, we want to identify which ones are equivalent. On my far left column, we have got values of pronumeral that we have, that is a. We have assigned a ranging from 0 all the way to 4. So the point here is to substitute at every given place the value of a in each and every algebraic expressions and find what values do we have. For example, looking at the first one here, 3a plus 5. But in this first column, if a is 0, then this one will mean that 3a, we shall substitute our a the way we did it in our previous class, where we shall have our a as 3 multiplied by a, and a is 0, then plus 5. That is what we shall have. So in this particular case, this one will give us 0 plus 5, which is equals to 5. So the first part here, we shall fill it with a 5. We shall fill it with a 5. Given that a is 1, it will be 3 times 1, which is 3, plus 5, which is 8. When a is 2, then we shall have 3 times 2, which is 6, plus 5, 11. When a is 3, it is 3 times 3 gives us 9. 9 plus 5, it gives us 14. And finally, given that a is 4, it is 4 times 3, it gives us 12. 12 plus 5, 17. So these are different values of the expression 3a plus 5, given that a ranges from a value of 0 all the way to 4. Let us move to the second algebraic expression, where we have 2a plus 6. Again, this is the way we have substituted in the first expression. We express the same in the second expression. So 2a plus 6, for the first part, it's 2 times 0, which is 0 plus 6. This one will give us 6. Then 2 times 1, when a is 1, is 2 plus 6. This one will give us 8. When a is 2, it's 2 times 2, which is 4, plus 6 gives us 10. Then when a is 3, it is 2 times 3 gives us 6. 6 plus 6 gives us 12. And finally, a is 4, so 2 times 4 is 8. 8 plus 4 plus 6, it gives us 14. So those are the values of the expression 2a plus 6 in this particular column, given that a ranges from 0 to 4. The next one here, we have got the same pronumeral a and a, but the terms here are 3. Take note that these other places, these are 2 terms, but these are 3 terms. But we shall substitute similarly the way we have done the rest. When a is 0, now in this case, we shall substitute a here and also there, such that this one is 7 times 0, and then this one is also 4 times 0. So 7 times 0 will give us a 0. We are to illustrate that for the 3. This one is 7 times 0, then plus 5, then minus 4 times 0. This is what we have. Any number multiplied by 0 is 0, so it means it shall remain with 5. So the value of this expression when a is 0 is 5. For the second part, when a is 1, we shall have 7 times 1 plus 5 minus 4 times 1. Again, this one gives us 7 plus 5 is 12 minus 4. That one will give us 12 minus 4 will give us so this one is going to give us 7. That is going to give us 7 for this one. That is 7 plus 5. This is 12 minus 4. This one gives us 8. So this part we shall have it as 8. When A is 2, this is 14. 14 plus 5 gives us 19. And then 19 minus 8 gives us 11. When A is 3, and when A is 3, we shall have 21 plus 5. That one gives us 26. Then 26 minus 12. When we subtract 26 minus 12, you will remain with 14. And for the last one, it is 4 times 7, which is 28, minus 5, giving us 23. Then 23 minus 16, which is going to give us 17. So these are the various values of this expression given the values of A ranging from 0 all the way to 4. For the last one, again, which you have 3 terms, it is A plus 6, which implies that when A is 0, it is 0 plus 0 plus 6, which is 6. Second part, it is 1 plus 1 plus 6, which gives us 8. The next one, it is 2 plus 2 plus 6, which gives us a 10. The next one, it is 3 plus 3, which is 6 plus 6 is 12. And the last one, 4 plus 4, then plus 6. That one will give us a 14. Now, looking at this, we can be able to simply identify which of these expressions are equivalent. Which ones are equivalent and which ones are not. I want you to look at the following. I want you to look at these expressions that we have here. This expression here and this. You look at the answers that we have for each case remains the same. When it was 0, it is 5 as well as 5 there, 8 and 8, 11 and 11, 14 and 14, and 17 and 17. What does that simply mean? It means that for this particular case that the expression 3A plus 5 and the expression 7A plus 5 minus 4A, these ones are equivalent algebraic expressions. So this expression and this other expression are equivalent. The same way, the second column and the fourth column, again, the two algebraic expressions are equivalent. That is 2A plus 6 and A plus 6. Both of them are equivalent. So what are we trying to say here? It is very important to note that equivalent algebraic expressions will always give us same answers when we substitute with certain values. So let us note this. We can simply, from what we have here, I want to say that two expressions or even more are said to be equivalent when they are equal. So we are saying that two expressions are said to be equivalent when they are equal, regardless of what numbers are substituted for the pronumerals. The pronumerals we had here was A, regardless of whether it was 0, 1, 2, 3, or 4, and so on, it remained that 3a plus 5 is equivalent to 7a plus 5 minus 4. That is what this statement is trying to tell us. And the same applies that the expression 2a plus 6 is equivalent to a plus 6, because whatever substitution you make, the answer is always the same. So we can simply conclude here by saying, we can have various expressions. We can simply conclude by saying some expression like 5x plus 2 is equivalent to 2 plus 5x. So you'll just realize it is a sum, and we have only changed the order. And when we change the order, there's nothing that is actually complicated in this particular case. It is just the same terms being summed up together. Now, and if you look at also, if we were to separate and say 1 plus 5x plus 1 as a terminology, as an expression, and also x plus 4x plus 2. Now, these four algebraic expressions, all of them are equivalent. And why are we saying they are equivalent? They are equivalent simply because when you simplify and bring actually, you simplify both the expressions together, you'll find that they simply form the same expression. And when you substitute at any given point, what you'll get is just the same. For example, this one will give us 5x plus 2. This one will give us, you bring it to 2 plus 5x. This one is the same as well as that. That is what it simply means. So let us look at a question on equivalent expressions. Now, here we are being asked which two of these expressions that we have are equivalent. And the expressions that we have is 3x plus 4, the first expression. Second one is 8 minus x, and the last one is 2x plus 4 plus x. Now, these are simply expressions independent. We said earlier on in the last statement that two expressions are said to be equivalent if, when you substitute the pronumerals with whichever number, the answer must be equal, which implies that we are going to pick a few and substitute them here, and then we see what do we get. And here, the easiest part to work out this is to make a table. You create the table, and then we assign some values and see what are we going to have. So let us have a table, and then on the table, we can have the following. So we have this table. As we saw in our last table, substituting, I've picked the values for us between 1, when x is 1, because the pronumeral in these expressions is x. So between 1 and 3. Among these expressions, which one will give us the same answer? So from the first one, it's allowed we would have started even from 0, but I've picked a few. So if x is 1 in the first expression, it will be 3 times 1, which is 3, plus 4, which gives us 7. The second one here, which will give us 8 minus 1, because x is 1, which gives us 7. The last one, x is 1, so 2 times 1 is 2, plus 4, this one gives us 6, plus another 1 gives us 7. So you realize that we are able to get 7 for each. But that does not mean that because we have all these 3 answers the same, then we can say all the 3 expressions are the same. No. We need to do other substitutions and see how the answers will respond. So let us move to the second one. We have x as 2. 2 times 3 is 6, and 6 plus 4 will give us a 10. Second one, x is 2, and we have 8 minus 2. When 8 minus 2, you'll find that you remain with 6. For the last one, when x is 2, it is 2 times 2, which is 4 plus 4 plus 4 gives us 8, and then 8 plus 2 gives us 10. And the last one, when x is 3, it is 3 times 3, which is 9. 9 plus 4, which is 13. 8 minus 3, which gives us 5. And finally, 3 times 2, which is 6, plus 4 gives us 10. Then 10 plus 3 gives us 13. From your own look, which of these expressions has constantly been giving us equal answer? Just look at what we have and tell us. So you will realize that the expression 3x plus 4 and 2x plus 4 plus x, these two expressions are equivalent. And if that is the case, why are we saying they are equivalent? Look at the columns. When x was 1, 2, and 3, it gave us 7, 10, and 13 for both cases, respectively. So you can simply conclude and say that 3x plus 4 and 2x plus 4 plus x are equivalent. So those are the two expressions which are equivalent. From the question that we have done, and I want to insist on this, do not substitute only one value across all the expressions and conclude that they form equivalent or they don't. It is very important that we do the substitution in various levels. So you don't always use just one substitution and conclude. We need to have several of them. Let us look at one more on the issue of equivalent expressions and see. So in this table, we are supposed to show that 6x plus 5 and 4x plus 5 plus 2x are equivalent by filling the table. Are equivalent by filling the table. So already what should be in our mind is that the two expressions are equivalent. What should happen is that you must be able to fill in and substitute correctly. If you don't do that, then you'll find that you are having different answers in these spaces, and then you conclude by saying, no, the two expressions are not equivalent. So while substituting, you must always confirm your answer. So let us look at it when x is 1. When x is 1, this is simply 6 plus 5, which is 11. And when x is 1 for the other one here, this one will give us 4 plus 5, which is 9, plus 2, which is 11. So for the first substitution, it has all given us 11. Let's move on to the second one. When it is 2, it is 12 plus 5, and 12 plus 5 is 17. And for this other case here, it is simply 8 plus 5 plus 4. 8 plus 5 is 13. 13 plus 4 is 17. So we have 17 there. When it is 3, we have 18 plus 5. And 18 plus 5 will give us 23. Where it's 3 times 6 is 18. 18 plus 5 is 23. And the other part we have 4 times 3. When you have 4 times 3, that gives us 12. 12 plus 5 gives us 17. And then 17 plus 6 will give us 23. And the last one, it is 4 times 6, which gives us 24, plus 5 gives us 29. And the other side, 4 times 4 is 16. 16 plus 5 gives us 21. Then 21 plus 8 gives us 29. So looking at the answers that we have, we are confidently sure that all these answers that we have are the same. Therefore, the two expressions proves to be equivalent. So anytime you are dealing with equivalent expressions, as you substitute the values, you must have the same answer. Now, let us look at one last, which is application bit of it. We have a rectangle. You all know what a rectangle is. It has got two opposite sides equals. So we have the length, which is opposite each other, and we have the breadth, which is also opposite each other. So we are saying this. The rectangle shown opposite has a perimeter given by B plus L plus B plus L. Question: write an equivalent expression for the perimeter. Write an equivalent expression for the perimeter. So what they are asking us here is to come up with another expression. In case we substitute the values of both the breadth and width, we shall always find, in case we substitute the values of both length and breadth, we shall always get the same perimeter. So here, it is very easy to work out on that, as we shall be looking at the next subtopic, where we simply combine the like terms. So in this particular case, you will either have it this way, or we can simply say another expression. These are 2b's, let us say 2b's plus 2l. Now this one and this one here are equivalent. They are equivalent. So by that example that I've given, then it is going to take us to another area that is simply related to this, which we call the like terms. So I want us now to go to the like terms and see how to move about when you have some expressions like this. Now, as we talk of terms in this particular case, when we introduced formal algebra, we went through the terms and the techniques used in algebra about pronumerals and so on. So when we have various pronumerals appearing several times and they are the same, those are the ones we normally refer to as like terms. Those are the ones we refer to as like terms. Now I want us to take an example of an expression and then we try to identify what are these that we are calling like terms. Now, this expression, 3x plus 5x, this is just a simple expression. It has got two terms. But when we try to simplify it, we realize that it will be simplified. When we simplify this, we shall find 8x. How are we getting this? It's simply because the pronumeral in the first term is x, and the same pronumeral in the second term is x. The sign or operation that connects these two is addition. Because this is x and this is x, then the coefficient of x here and the coefficient of x there are simply added because we are adding, just the way we do it in ordinary addition and subtraction of integers. So we shall add, this is 3x plus 5x, and that one gives us 8x. Then, why are we doing this? We are doing that because x and x here is what we refer to as like terms. So we are able to simply add or collect what we call the like terms. Look at this other example, and this one now I'll bring in other additional terms where we shall be required to collect what we think are like terms. Now, precisely, this is what we have. We have two terms here, different. We have A's, we have B's. While collecting or simply adding like terms, we look at those which are alike, are those ones which have the same letter representing it as a pronumeral. So in this case, we have A and we have B. So A and other terms which have got an A are brought together. So I'll expect you to have 1A plus 3A plus 5A, then plus 2B plus 6B. So those are the ones which are brought together. So you realize these are like terms, these are like terms. When you do that, this is 1A plus 3A, which gives us 4A. 4A plus 5A gives us 9A, then plus, this gives us 8B. Now, they are not, because A and B are not like terms, when simplified, they'll remain the way they are. You cannot combine them. You cannot add them up. A and B are not like terms. They cannot be added. But A and A can be added and can be subtracted. B and B can also be added and subtracted. So that's why when we simplify this expression, we shall stop at this point. We cannot simplify this further. So when we talk of like terms in general, like terms in general are as follows. So we are saying this. Like terms are terms containing exactly the same pronumerals, although not necessarily in the same order. When we talk of not necessarily in the same order, I want you to look at this. 5AB. Well, how many pronumerals do we have in this particular term? We have got two pronumerals. One is A, another one is B. And we will take 3BA. Sorry, before we get to that, 3AB. We shall simply say that these are like terms. But supposing the same, we were to change. Instead of writing 3AB, we write 3BA. We have said not necessarily in the same order. So AB and BA simply means the same. So we shall still say this and that are like terms. If you look at this 4A plus 7B, 4A, not plus, but and 7B, when you compare these two, then 4 has got its pronumeral as A, and B has got its pronumeral as B, then, and that is the second one as B, then we shall say this one are not like terms. And they are not like terms. Why? Because we say like terms must contain exactly the same pronumerals. That is, this one has A, this one has B, so they are not alike. But for this one, it was AB, AB, or it was AB, BA. There's no difference. They are like terms. For those with three pronumerals, for example, if we look at 2ACB and we compare this 4BAC, what do you think about this? Are they alike or they are not like terms? Can you look at it? Now, for this particular case, we shall say they are like terms because we shall look at this last statement. Not necessarily in the same order. The order here is ACB. The order here is BAC. And you are saying the pronumerals here are A, B, and C. Pronumerals here are A, B, and C. So these are like terms. These are like terms. So that is the first observation we need to make when we are talking about like terms. The next observation that is important is as follows. Like terms can be combined. Like terms can be combined. We find that like terms can be combined. In this particular case, if we are to combine the like terms, how do we go about it? So we are saying here that like terms can be combined within an expression to create a simpler expression that is equivalent. So like terms can be combined to simply come up with a simpler expression, and that expression is an equivalent expression. Let us look at this. Now, when you look at this, 5ab plus 3ab. First, we identify, are they alike or they are not like terms? We shall find that they are simply like terms. If they are like terms, then we can go ahead and simply combine them. 5ab plus 3ab can be combined within an expression to create another simple expression, which is 8ab. And 8ab is an equivalent expression of these other two. So we have been able to combine. That's why we say terms can be combined. The last point to note when we are looking at what we call like terms is as follows. Now, we are saying that if two terms are not like terms, for example, 4x and 5y, they cannot, so they can still be added to get an expression like 4x plus 5y, but this expression cannot be simplified further. So it will be simplified, but it will remain with the two terms. So in dealing with like terms, those are the serious 3 points that we must always observe. As we go into the questions now here, we shall maintain the 3 points that we have looked above. So let us look at the following questions. So which of the following pairs are like terms? We shall handle each so fast, quickly. 3x and 2x. The pronumeral here is x. The pronumeral, the second term is x. So these two terms are like terms. The two terms are, this one here gives us like terms. Second one, we have 3a and 3b. Because one is a, another one is b, then this one are not like terms. The third one is 2ab and 5ba. In our points to note, we said the order doesn't matter. BA and AB will always be like terms. So we shall say that these 2A and 5, these 2AB and 5BA are like terms. This is just straightforward, 4K and K. The coefficient here is 4, the coefficient here is 1. But the main part is because K and K is the same pronumeral, then this gives us like terms. And then 2A and 4AB. This one we have two pronumerals. Here we have one pronumeral. So these ones, the two terms here are not like. Simply because this is AB and the other one is A. The last one is 4AB, 7AB and 9ABA. Now this one is tricky, but we need to look at it. How many times is a pronumeral appearing? Now here it is 7AB and this one is 9ABA. If you were to look at this again, you realize that this is almost the same as to say it is 7a squared b, because this is appearing twice. So this one and this one do not form the same because a and a squared are not the same terms. So we can conclude here and say not like terms. So if they were asking us to identify which pairs are like terms, so we have the pairs 3x and 2x are like. We have 2ab and 5ba are like. 4k and k are like terms, and the rest are not. So we have the 3, and the rest that are remaining are not like terms. So we have two questions here. Simplify the following by collecting like terms. We are going to collect like terms. The first one, 7b plus 2 plus 3b. And the last one is 5 plus 12a plus 4b minus 2 minus 3a. So looking at the first one here, it is 7b plus 2 plus 3b. You'll notice that 7b and 3b share like terms, so we shall collect them together to have 7b plus 3b. We shall maintain the sign and then minus plus 2. 7 and 3 combines to make 10b, then plus 2. This one, when we collect like terms, we shall get 10b plus 2, 2 as a constant. 10b plus 2. For the second part, we have 5 plus 12a plus 4b minus 2, then minus 3a. Now, we collect like terms. Constants comes together. So this is 5 minus 2 plus 12a minus 3a, then plus 4b. That will be when we collect. So 5 minus 2 gives us 3. 12a minus 3a, that one will give us 9, so it will be plus 9a. And then we have the last one plus 4b, plus 4b. So reaching here, we cannot simplify this expression any further. So we shall say, when we collect like terms here, we shall get 3 plus 9a plus 4b. So that is it for our lesson today. In our next class, we shall be looking at multiplying, dividing, mixed operations. Thank you.